Good evening, class. This is a lecture on electron configurations, and we'll also go into periodicity, or the periodic behavior of the elements. In our last chapter, we talked about the quantum numbers NL and ML. There's also a fourth quantum number, which we'll call the electron spin quantum number, which is abbreviated as M with a subscript S. And MS will have values of plus 1/2 and minus 1/2, something of a relief from the integers that we were using for the other quantum numbers. And MS is related to the small magnetic field produced by rapidly spinning electrons. Before going into that, this is all to add to the story that the chemical properties of elements depend upon the number and arrangement of electrons in an atom. We'll show that not only the elements, but also the ions that are formed from the elements depend upon their electron configuration. Okay, back to magnetic properties. A substance can interact, or some substances can interact with magnetic fields and others do not. In general, substances can be characterized as being either diamagnetic, which means that they do not interact with a magnetic field, paramagnetic, meaning that they are attracted or they do interact with a magnetic field, and ferromagnetic, which are those substances that are permanent magnets themselves. So it was determined that certain elements, in fact several elements, are paramagnetic. That is, they will respond to a magnetic field. And as a way to explain that, this additional quantum number was conceived. These magnetic properties depend on whether or not a substance does not have unpaired electrons. This is because a charged electron is actually spinning very rapidly. And as you probably know, a spinning charge produces a magnetic field. And likewise, a spinning magnet produces an electric field. This is the basic theory of electromagnetics. So if we have an electron and it is spinning, and we bring in an external magnetic field, that electron will either spin pointing in the direction of the magnetic field or opposite the direction of the magnetic field. And these two orientations for the spin of the electrons, we characterize as plus 1/2 and minus 1/2. So let's consider a hydrogen atom. Hydrogen atom has a single electron. Now this is not diatomic hydrogen, but the monoatomic hydrogen atom will have a single electron. And if we place that electron in the lowest energy level, energy levels that we described in the previous lectures, we would put that electron in the 1s orbital. N equals 1 and the s orbital. If there's a single electron, so we would have one electron in 1s as shown in the bottom left hand. And we generally represent these electrons as arrows. And so if we arbitrarily have that arrow pointing up, this would be the representation for the hydrogen atom. It would have a single electron. Now that single electron, again, because it is spinning, would interact with a magnetic field. And so the hydrogen atom would be paramagnetic, would interact with the magnetic field. If we then go to helium and we bring in a second electron, that second electron will also fill into the 1s orbital, but it will be pointed in the opposite direction or spinning in the opposite direction. Okay, we would say that the two electrons in the 1s orbital are paired. Now, when they are paired, that leads to the condition of being diamagnetic. So a pair of electrons is diamagnetic, unpaired is paramagnetic. This can also be described by what is called the Pauli exclusion principle after Wolfgang Pauli, who stated that no two electrons in an atom can have the same set of 4 quantum numbers, N, L, ML, and MS. The consequence is that you can have only 2 electrons in a given orbital. For example, an electron may have N equals 1, L equals 0, ML equals 0, and MS plus 1/2. That would be a set of 4 quantum numbers. The other electron would have to have MS equal minus 1/2. So let's consider the lithium atom. We talked about the hydrogen and helium. Let's build up and talk about the lithium atom. The last electron in the lithium atom is actually going to go into n equals 2, energy level 2, L equals 0, which is an s orbital, Ml equals 0 because there's only one type of s orbital, and the first electron we would say has ms, this fourth quantum number, of plus 1/2. Okay, another example, the ninth electron that fills, that is added to form fluorine. What would the quantum number be for that last electron? Well, it would actually be, we're filling n equals 2 again. This time we're filling into the p orbital set, that's L equals 1. We're adding to one of the individual p orbitals, which arbitrarily we could say is either the -1, the 0, or the +1 ml value. And we would say it has an ms value of -1/2, or just opposite of what the other electron is in that particular orbital. The complete electron configuration of the atom can also be written, or can be written in what we call spectroscopic notation, which is sort of a shorthand way of writing out the electron configurations by listing the orbitals that are filled and indicating the number of electrons in that orbital subset. For example, let's look at fluorine and scandium. Fluorine has 2 electrons in the 1s orbital, 2 electrons in the 2s, and it has 5 electrons in the 2p. So we would say it's 1s2, 2s2, 2p5. Scandium, likewise, is 1s2, 2s2, 2p6. That is completely filled rows 1 and 2. And then we would say it's 3s2, 3p6, filling row 3, 4s2, 3d1. In the next slide, we'll talk a little bit more about scandium, and we'll see why it filled in that order. But this gives examples of the way we write things out in spectroscopic notation. So let's look a little bit more at some important set of elements. Potassium, element 19, calcium 20, scandium 21, and then others in that same row, titanium, chromium, manganese, and copper. For potassium has filled the orbitals 1s2, two electrons in the 1s orbital, 2s2, 2 electrons in the 2s orbital, 2p6, filling row numbers 2, and then 3s2, 3p6, and then we go to the fourth row, 4s1. This is as we would expect. Calcium, likewise, as we would expect, is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. Okay, and we've paired up all of the electrons in each orbital. We've paired up the electrons in the 1s, the 2s. We filled completely the 2p. We filled up both electrons in the 3s. We filled up completely the 3p, and also 2 electrons in the 4s. Now, if what I'm saying is going a little rapidly, you know, you can always stop, back up a little bit, and watch it again. Okay, scandium. Scandium actually is, as we said in the previous slide, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now 3d1. Okay, well, what's happening? Well, if you remember in the last slide or two of the previous video lecture, we said that something odd happens when we go between energies levels 3 and 4 because the actual energy level of the 4s electrons is lower than the energy level of the 3d electrons. That's why in potassium and in calcium, we didn't go from 3p6 to 3d. We drop down and we put that next electron in 4s1 and then 4s2. But finally, when we get to scandium, we fill the next electron, the 21st electron, into 3d1. So again, scandium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d1 as a single electron in a 3d orbital subshell. Now, would scandium be paramagnetic? Yes, it has a single unpaired electron. Would calcium? No. Would potassium? Yes, because it has a single electron in 4s, 4s1. Now, as we continue on to titanium, the next element in the periodic table after scandium, we continue to add to the 3d orbital set. And we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now 3d2. Now, for that 3d2, remember we have 5 3d orbitals, and we're actually not pairing up those 2 electrons in the 3d2. They're not paired up. There is 1 electron in one of the 5 3d orbitals and 1 electron in one of the other 3d orbitals. Okay, so titanium, even though it might look like everything is even, titanium actually has 2 unpaired electrons, and it would be paramagnetic. Chromium. Chromium and also copper. Something strange happens. These elements choose to form half-filled or completely filled 3d orbitals by recruiting 1 electron from the 4s set of electrons and moving that electron to either half fill the 3d orbital subshell or to completely fill the 3d orbital subshell in copper. So in chromium, we wind up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. We have as many as 6, that is the 1 in 4s1 and the 5 in 3d5, as much as 6 unpaired electrons in chromium. Very paramagnetic. Okay, again, chromium does this. This is not expected, but chromium does this to have a half-filled 3d5 orbital subshell, leaving behind just a single electron in 4s1. Now, when we go to manganese, the very next element, we add 1 more electron, and it goes back into 4s to pair up 4s2. As we said, when we go to copper, the same type of thing happens. You might have expected copper to be 4s2, 3d9, but instead, it recruits 1 of the electrons in 4s2, bringing it into the 3d orbital to form 3d10, a completely filled 3d orbital subset or subshell, leaving 1 unpaired electron in copper, in the 4s orbital of copper. You add 1 more electron to form zinc, you pair up the 4s to form 4s2, and zinc is diamagnetic. Now this slide shows an alternate way of drawing out these same elements using a sort of a box method. And this shows the electrons and whether or not they're paired up or not. So in the previous slide, you had to visualize whether or not the electrons were paired up. Here we show you. For potassium, I give the electron configuration on the left, and on the right, I show this box diagram where you can see it's 1s2, 2s2, 2p6, 3s2, 3p6, and a single electron in 4s1. Scandium, same thing, 1s2, 2s2, 2p6, 3s2, 3p6. At some point, you'll be able to say these things as quickly. And in 4s2, 3d1, a single electron in 3d. Titanium, as we said, is 3d2. The very last 2 electrons go into the 3d orbital, but they are spaced out 1 electron in each of 2 different 3d orbitals. Okay. Chromium, remember we said that something funny happens with chromium and with copper. This is a representation of what happens with chromium. With chromium, we wind up with the last sets of electrons being 4s1, 3d5. That's so that you can have a half-filled, and if you look over to the right, a half-filled 3d5, leaving behind only a single electron in 4s, 6 unpaired electrons. You add another electron to form manganese, it pairs up the 4s to 4s2, but it still has 5 unpaired electrons in 3d5. And then copper also recruits an electron from 4s2, leaving 1 unpaired electron in the 4s, and winding up with a completely filled 3d5 orbital subset. Okay. Now, the examples we gave in the previous slide, especially ones like titanium, where we show that we spread the electrons out into individual 3d5 orbitals. And we also do this with the p orbitals. just didn't mention it or stress it at the time. This can also be referred to as what is called Hund's rule, the tendency of electrons in a given subshell to spread out in an unpaired manner before pairing up. The pairing of electrons actually requires some repulsion between electrons. Remember, electrons are negatively charged and they repel each other. So to put two electrons in the same orbital leads to a little bit of repulsion, and they'd rather be spread out if given a chance. So if we have a p orbital set or a d orbital set, we could have like 3 unpaired electrons in a 2p or a 3p orbital subset, and we can have as many as 5 unpaired electrons in a d orbital subset. In the middle of this slide, I'll just show again that the ML values and the spectroscopic notations are alternate ways of labeling the individual orbitals. So using the ML representation, we could say we have -1, 0, and +1 ML values, or we could call these PX, PY, PZ. Now it's arbitrary of which one we call PX, PY, PZ with respect to relating to -1, 0, and +1. They're just different labels. And similarly, for the d orbitals, we can label these -2, -1, 0, +1, or +2. Or we can call them by these other descriptors, dxy, dxz, dyz, dz squared, and dx squared minus y squared. Yet another handy shortcut for describing electron configurations, such as for scandium. We can write out scandium as shown near the bottom as 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, 3d1. We can go through all of that. Or we can note that the first part, the 1s2, 2s2, 2p6, 3s2, 3p6, all of that part is just the electron configuration of the nearest noble gas, which happens to be argon. So we can say it's all argon plus 4s2, 3d1. Okay, so that actually is simpler, and you are allowed to do that. Okay. Right, now let's talk a little bit about ions and their electron configurations. Much of chemistry involves the ions of the elements. And ions are formed by either gaining or losing electrons, with the tendency being to try to form the electron configuration of the nearest noble gas. Let's look at examples of sodium forming sodium cation and sulfur forming sulfide S-2. So sodium, if it loses an electron, will form sodium plus, sodium cation. Okay, so sodium itself as an element would have the electron configuration of 1s2, 2s2, 2p6, 3s1. If it loses an electron, it will lose the electron in the highest energy level. That would be the 3s1 orbital, the one that's furthest from the nucleus. If it loses that 3s1 electron, it now would have the electron configuration 1s2, 2s2, 2p6, which is a completely filling rows 1 and 2, or in other words, having the electron configuration of neon. Now, since there are 8 electrons in row 2 and also in row 3, we often describe this as in terms of the octet rule of trying to form an electron configuration with 8 electrons in the outer shell, although sometimes it's 18. Sulfur. Sulfur forms an anion by gaining 2 electrons from somebody else. Sulfur itself has the electron configuration of 1s2, 2s2, 2p6, 3s2, 3p4. If it gains 2 electrons, where does it put them? It puts them in 3p4 to form 3p6. 1s2, 2s2, 2p6, 3s2, 3p6, completely filled rows 1, rows 2, rows 3, or sulfide, the anion of sulfur, has the electron configuration of argon. Okay. Now, forming cations from the D block or the F block, and we won't really get into the F block elements, but forming a cation from the D block elements is a little more complicated. Let's give some examples, though. Generally, we lose the 4s electrons first, and then possibly one or more of the 3d electrons. And remember, a half-filled or a completely filled 3D orbital subset has some stability. So let's look at iron. You may know that iron tends to form cations of either +2 or +3. To form a +2 cation, it would lose 2 electrons. So to the left, I show the electron configuration of iron, and I'm going to take the shortcut by using the square brackets argon, saying everything that is argon plus 3d6 4s2. Now, parenthetically, I could have written this 4s2 3d6. I don't mind so much whether or not you call it 3d6 4s2 or 4s2 3d6. Some people do, I don't. So you can essentially write that either way. But if you lose 2 electrons, you will lose the 4s electrons first, leaving behind 3d6. And so we say that iron +2 has the electron configuration of argon 3d6. If it loses one more electron, it will lose one of those 3d6 electrons and now be 3d5. And as we said, 3d5 has a half-filled 3d orbital subshell, and there's a little bit of stability in having a half-filled or a completely filled 3d orbital or d orbital set. Copper. Copper, if you remember, something funny happens with chromium and copper. Copper is argon 3d10 4s1. It tends to lose 1 electron very easily to form copper +1, and if it does so, it of course loses that 4s1 electron to give argon 3d10 as copper +1. It can on occasions lose a second electron to form copper +2. In doing so, it loses one of the electrons from the 3d10 to form 3d9. But among all of the elements, copper and the ones below it, including silver, are the ones that tend to form +1 cations with a significant tendency, whereas most of the other elements in the transition metal area form +2, +3, and higher cations. One more example. Manganese. Manganese is argon 3d5 4s2. It tends to lose 2 electrons to form manganese +2. It actually tends to lose as many as 7, but if it loses 2, its electron configuration will be manganese +2 will be argon 3d5. Okay, now a type of question to prepare for is I might ask you, which of these elements or which of these cations is diamagnetic, which are paramagnetic? And if you look at the bottom row, can you see any that would be diamagnetic? I'll give you a second. Do you see any that would be diamagnetic? Even though some of them look like they're even numbers, like iron itself, 3d6, but remember they're spread out so that there are a number of unpaired electrons in that 3d6. Iron +2, likewise, 3d6 spread out. 3d5, they're all spread out, 5 unpaired electrons. Copper +1. Copper +1, argon 3d10. 10 electrons, 2 each. They're all paired up. 2 each in the 3d orbital subset. Yep, that's the only one on the bottom of the page. Of course, on the top of the page, both the sodium cation and the sulfide anion would be diamagnetic. Note that magnesium +2, sodium +1, fluoride -1, oxide -2, and nitride -3. These are the cations and anions of these species, are all what we call isoelectronic. That is, they have the same number of electrons as neon. Turns out to be 10 electrons. We'll show that a little bit more in the next slide. I think I have that illustrated a little bit more. But before going to that, let's look at the periodic table. And we now should realize that the organization of the periodic table is laid out in the following way. To the left, the first 2 columns or groups are the S block elements. Then in the yellow, in the middle of the periodic table, we have the D block elements. That is, the last electrons are generally adding to the D orbital type. And then over to the right, we have the p block elements, where the last electrons being added are being added to p orbitals. And at the bottom, the lanthanides and actinides are actually part of what we call the f block elements. Okay, we'll pause now so that this lecture doesn't go on too long, and then we'll continue and talk about periodicity in the next video lecture.